So we had seen that for a reaction like this, for a reaction like this, the equilibrium constant is given by the equilibrium constant Kc is given by concentration of C, capital C, raised to the power stoichiometric constant, concentration of D raised to power its own stoichiometric constant divided by the product of the concentrations of reactants raised to their individual stoichiometric constants. Fine. Okay. So for a reaction like this, after it is balanced, okay, after it is balanced, we get Kc as Hi whole square divided by concentration of H2 multiplied by concentration of I2. Fine. What if the reaction becomes the reverse of what it is? Okay. If the reaction becomes the reverse of what it is. So for example, instead of this, the reaction is this.
It is an equilibrium, why would it go reverse?
It can, I'll tell you. I can start from the products, right? It will settle back to the reactants, correct? It's not essential that you start with H2I2 to get HI. You might as well start from HI and you'll get back H2I2. After all, it's an equilibrium, right? Okay. So this, it's quite simple. Say if I call it Kc dash, then that is equal to, right? By the definition of equilibrium constant, it becomes this. Okay. So it becomes this. Now, if you just compare them, then you find it is 1 upon Kc. Okay. So equilibrium constant for the reverse reaction will be the reciprocal of that for the forward reaction, right? So we write that equilibrium constant for the reverse reaction is reciprocal of the equilibrium constant in the forward direction for the same reaction. Okay, for the same reaction. Okay. Now what happens if you change the stoichiometric constants by multiplying it by some constant? I can always do that, right? for a balanced reaction, I have a balanced reaction, I multiply both the sides by the same constant. It still remains balanced, right? However, I'd like to make an important distinction. When you are finding out the equilibrium constant, you do it for the balanced reaction which has got minimum multiples, right? Because that will now confuse you. So what happens? Let us say I have this reaction. I have the same reaction, okay? So I'll be dealing with multiplying a reaction
If we do multiply it, then
with a constant.
will it give us a different value?
Let us see. Okay, so AA plus this CC plus DD. Okay. Now, if I multiply both the sides by n, so then what happens? This becomes n, this also becomes n, this becomes n, this becomes n. I'll put back the plus signs, right? Or hold on. Multiplying by n we get, multiplying by n we get. What happens? You have AA, okay, plus this giving us this, okay. Now that gives us this, okay, the green ones, the n's come in. Now it's very simple, okay, just attempt on your own. What is the equilibrium constant for this? Say let us term it as Kc dash, okay, let us term it Kc dash, Kc double dash, fine. This has nothing to do with the derivatives, otherwise dashes stand for derivatives, it's not a derivative. So this is equal to concentration of C raised to the power the stoichiometric constant into concentration of D raised to the power this divided by concentration of A raised to the power Na, concentration of B raised to the power Nb. Okay. Now, if you look at it, it becomes equal to this raised to the power n, is it not? And this is what? Kc, so it becomes Kc to the power n. Okay. Now that significantly alters Kc itself, the equilibrium constant for that reaction. And equilibrium constant is something that is indicative of what will be the direction of the reaction, right? That will tell you how much of product you will be able to get, whether the reaction moves in the forward direction at all, okay, mathematically. Now if I keep on multiplying this by some constant, say 1,000,000, okay, then it will give you some other value altogether. Now does it mean that the equilibrium has shifted just because I have multiplied both the sides by a constant and the reaction is still balanced? The answer is no. Why? Because the equilibrium constant that you use for judging whether the reaction has moved in the forward or the reverse direction is not this, but the minimum multiples which are required for balancing the reaction. Okay, you should keep that in mind. Otherwise, suddenly the whole interpretation will change. We'll soon come to that. Okay, for example, any value of Kc that is greater than 1000, it is considered that in the equilibrium there will be predominantly products, and anything that is less than 10 to the power minus 3, it means it is predominantly reactant. Anything between it is considered, it's a ballpark, it's kind of an approximate sort of figure that has been set in, right? There is no logic to whys of this. But the thing is, if it is between 10 to the power minus 3 and 10 to the power 3, then you consider that there is a considerable amount of comparable amounts of reactants and the products. Okay. Now let us try to understand a situation where Kc is equal to 2. So what is your interpretation? That comparable amounts of reactants and products are available. Okay. Now what happens? You multiply both the sides by say 20. Now suddenly what happens? It will become 2 to the power 20. Okay. Now 2 to the power 2 to the power 4 is 16. Okay. So 2 to the power 8 is 256. Okay. Okay, and 2 to the power 10 is 1024. So 1024 into 1024, suddenly it becomes say 10 to the power 6 or something. Now your interpretation changes from comparable amount of reactants and products to predominantly products. Okay. Why this anomaly has crept in? Because instead of the minimum multiples that were required, you have imposed your own multiples, and by the very definition of the equilibrium constant, that has got raised to the power whatever constant you have multiplied with. Get the point? Get the point? So for judging whether the reaction has proceeded in what direction or where it is, you will be using the normal balanced equation that you have been doing in class 10th. And that is with the minimum multiples. Okay. Even otherwise, you see, while balancing the equation, you do not sort of start multiplying it by 2000, 5000, 10,000. No. Right. You stay at the minimum. It is like the conventional notation of the fractions where you do not tolerate 2 upon 4. You say no, everyone has to write it as 2, 1 upon 2. No, you have to cut the common terms. Why? Because otherwise it can become very misleading, right? Someone says 1, 2, 1, 2 upon 2, 4, 2, 4. Now it will take you some time before you realize that it is actually 1 by 2. Is it not? Okay. So that's why this convention has been put in. In the same manner, you can think that the criterion for minimum multiples has been put up, right? Otherwise, the same balanced equation can appear in so many forms by so many people. Correct. And it will be pretty difficult for people to understand whether it is the same balanced equation, or maybe you put some weird numbers, right? After balancing, you multiply it by 1, 2, 5, 7, 9, both sides. Right. It will require hell amount of task comparing the, say, the hydrogens, the oxygens, then you multiply everything by 1, 2, 5, 7, 9 and then check. Fine. So though technically, theoretically it becomes that, okay, we are exploring all the possibilities, but for judging what has happened to the reaction, okay, which is one of the most powerful things of Kc, right? That is one of the applications of Kc. Okay, it is used as a parameter for checking whether the reaction will proceed in a particular direction. Fine. Okay, but we keep in mind that We'll never use the multiplied versions. We'll use the minimum multiples. So we say that the that if we multiply both sides of the reaction, both sides of the reaction by a constant n, of the balanced reaction by a constant n, then the new equilibrium constant becomes the old equilibrium constant raised to the power n. That is Kc double dash is equal to Kc to the power n. Okay? Do we understand? So you should be kind of telling the form of the equation before before deciding on values, right? So this is Kc, Cc, Td, Aa, Pb. This is 1 upon Kc, right? N. Okay, so these are the reactions and the equilibrium constants. Pretty mathematical, right? It's pretty mathematical, right? So this is the summary of what we have been saying. Okay, fine.